In this video, we're going to be taking a look at two masses connected by a massless rod, and we're going to take a look at all the forces acting on them and then solve for the acceleration of the system and then also the tension of the rod in between them. So we have a 30-degree incline and a coefficient of kinetic friction of 0.25, which we're going to need a little bit later. Now, the first thing we're going to want to do is we're going to want to take our system and create a little boundary around it. And let's just treat it like a big 7-kilogram system as opposed to a separate 3 and 4 kilogram system. All right, so let's go ahead and draw our forces acting on it. We, of course, have the force of gravity going straight down. We have the normal force up perpendicular from the surface. And then we also have the force of kinetic friction opposing the slide as it goes down the ramp. Now, as we normally would, we have two different axes, everything that is parallel to the ramp and everything that's perpendicular. So our FG is not in that category, so we want to break it up into two components, which we're going to call the FGY and the FGX. Okay, and we have our 30-degree angle translated into that part of our triangle. Now, because we have FGX opposite of this 30-degree angle, and we do have FG because we know FG is mg, mass times 9.8, we know that our FG is going to be 68.6 newtons. Okay, so that's going to be the hypotenuse of our triangle, and then we want the opposite end for our FGX. So for our FGX, we're going to end up doing 68.6 newtons times the sine of 30 degrees, and then that's going to give us 34.3 newtons. Now for our y component, we're going to do something very similar. We're going to go ahead and use the hypotenuse again, the 68.6, except we have the adjacent side to our 30-degree angle. So we're going to replace this sine with a cosine. So for the FGY, it's 68.6 times the cosine of 30 degrees, and then that leaves us with an FGY of 59.41 newtons. Okay, now when we create our formulas, we're going to have one formula for the y-axis or the perpendicular axis, and then we're going to create one formula for our parallel axis or our x-axis. Now for our perpendicular one, we just have Fn going up, subtracting FGY going down, and we know that equals 0 newtons because there is no movement or acceleration in the perpendicular direction. So it's basically just telling us that Fn is equal to FGY, and we already know FGY is 59.41 newtons. So we basically have both of those. Okay, so our main focus is actually going to be everything in the parallel direction because the parallel direction is the thing that's going to give us our acceleration anyways. So in the parallel direction, we have our FGX driving our masses down the ramp. We have the force of kinetic friction slowing them down, and that is equal to the mass of the entire system, which is 7 times A. Now for our FGX, we did already get that. That is 34.3 newtons. And then for the kinetic friction, it is mu times normal force for the formula. So we're going to take our mu and take our normal force and find the product of those two. Our mu is 0.25, the coefficient of kinetic friction that we got earlier in purple. And then we know our Fn is 59.41 that we got a little bit earlier too. Okay, so now we basically have everything we need. We're going to go ahead and sum up everything on this side. And then divide both sides by 7 to cancel out this 7 over here. And that's going to give us our acceleration. And our acceleration comes out to 2.78 meters per second squared. Okay, so let's go ahead and put that right here. Now for the second part of our problem, we're going to go ahead and find the tension of the rod. So let's go ahead and clear a little space and then go ahead and solve for that tension. Now when we solve for tension, we're going to have to look at one of the masses individually. The reason why we have to do that is because we took a look at the system as a whole. So the rod was an internal force, which means it's not included in any of our formulas. So we can analyze the 3 kilogram or the 4 kilogram object. Either one would be totally fine. But let's go ahead and grab our 4 kilogram mass. And if we're just focusing on our 4 kilogram mass, we of course have the force of gravity straight down. That has the two components as it did earlier, the FGY and also the FGX. We have the normal force up perpendicular from the surface, and then we have the force of kinetic friction pushing back on the object. In addition, because the rod is connected to it, there is an FT opposing its slide as well. So it's working together with the FFK to oppose that FGX. So let's go ahead and create a new formula. We have our FGX of our 4 kilogram mass minus the FT and the FFK. So just like we did with the previous one, we're going to need some components. So we're still going to use the 30-degree angle over here, and then our FG is going to be the mg, which is 4 times 9.8, because we're focusing on the 4 kilogram block at this moment. And that is 39.2 newtons. So if we go ahead and plug in all of our variables, oh, I forgot to complete this one. So all this equals MA, but we're just looking at the 4 kilogram one. So that's 4. And then we actually already have the A. It's 2.78 meters per second squared. That's the one that we got earlier for the entire system, which is a big help to solving this part of it. Now we can go ahead and plug in all of our values and then see what we get for FT. Now that we're just about done with this problem, we have our FGX, which we did something similar to what we did with the first triangle, as we used the sine of the angle times the hypotenuse to find our FGX. We subtracted FT. FT is our unknown. And then we did the coefficient of kinetic friction times the normal force again for the kinetic friction for this case. Okay, the difference is instead of taking the 68.6 newtons for the 7 times 9.8, we took the 39.2 for the 4 times 9.8, and then multiplied it by the cosine of 30. The cosine of 30 gave us FGY, which is equal to Fn. So they're basically the same exact thing. Now, when we calculate the numbers, we get 19.6 minus FT minus 8.49 equals 11.12, which are obviously values that are going to be rounded off a bit. If we add 8.49 to each side, we end up with 19.61, and then we have 19.6 minus FT equals 19.61. Now, if we subtract 19.6 from both sides, we end up with 0.01 newtons. Okay, and the reason why that number is so small is that it's actually supposed to be 0, but because of rounding, it doesn't end up being 0.00 newtons on the dot. Okay, so our final answer for the force of tension is about 0 newtons. Okay, why is it 0 newtons? In order for there to be tension in the rod, these two objects would have to be accelerating at different rates. Now, if they are on the same incline with the same coefficient of kinetic friction, all masses are going to have the same acceleration because the masses actually drop out. So because the 3 and the 4 kilogram mass are accelerating at the same rate, there is no push or pull in the center here because both of them are moving equally. They keep that space equal between each other without the 4 tugging a little extra by accelerating faster or by pushing back by accelerating slower than the 3. So in the end, there is no tension in this massless rod. So I hope that was helpful to you in finding the acceleration of the system and the tension of the rod. Thank you for watching and listening.